All right, so we're going to do section 3.2. It's going to be a really short section. There isn't a whole lot in it, but we're going to do a little bit with graphs in it and just some overall rules for derivatives on here. So 3.2, the title doesn't really tell you that much. The title is Working with Derivatives. We're going to go over some of the basic rules, and we won't see these rules that much until probably chapter 4, really, but we're going to learn just a couple basic rules of our derivatives. So everything starts with what we're calling f, which is the original function. Okay. Now, if I want to find the rates and the slopes of that function, what we would then find is we would find the derivative function. And so we call that f prime, and that means it's the first derivative. Okay? The derivative of f. And we really could even go further. I could have more than just f and f prime. I could even have f double prime and I want. And this is the derivative of f prime. Okay? So every time that you find one more derivative, you just keep adding primes to it. All right, so let's practice sketching graphs. So example 1, we are going to go ahead and sketch the graph of f prime from the graph of f. So I'm going to give you a graph of f, and then you're going to have to sketch the graph of f prime. All right, so we're going to have a long y-axis here, and it looks like you need to go out to 5 on the y-axis. Excuse the dog barking in the background. And I'm going to have this x-axis go up to 4, and then down to, -1 or -2. All right, so I'm going to tell you 4 points to put on the graph. We're going to put the point 2, 1. Then we're going to have the point, I think I messed up, 2, 2, excuse me, 2, 2, -2, 2, geez. Then we're going to have the point 0, 4, 2, 3, and I think that's it. Nope, 4, 2. One more point. We're going to put the point -3, 3. All right. And we're just kind of going to connect everything with line segments. All right. This is the graph of f that was given to you. Your instructions are to graph f prime. Now, remember, the derivatives are all the slopes. And luckily, these are all linear functions. So if you just think about it, let's say that the original function is 3x. Without having to do all that work, what's the derivative going to be? Okay, well, remember, the derivative is going to be the slope of that function. So the slope of that line at any time, it doesn't matter where you're at, the slope is always going to be 3. So while the first one was a linear function with a positive slope, how do you graph the derivative function? How would I graph 3? Well, y = 3 is a horizontal line. So you would just go up to 3 and draw a horizontal line there. So because these are all linear functions, the derivatives are all going to be constants. I'm going to be graphing a bunch of horizontal lines. Okay, so we don't know the original equations, but I can find the slope of every point. So we're going to do rise over run. So first, let's find all the slopes. Right away, I'm seeing that this second half is down 1, right 2, down 1, right 2. So this first line has a slope of -1/2. Okay, this line here has a slope of up 2 over 2. So that one has a slope of +1. This one over here, to go from this point to this point, I have to go down 1, right 1. So that's -1. So I'm going to graph all these slopes. Now, we have to be really careful because they're on different intervals. So I am going to draw another graph this time. Now, my derivative is going to be a horizontal line of -1/2. So f prime equals -1/2, but on what interval? And that interval looks like to me from 0 to 5. So from 0 to 5, I'm going to just put a little tick mark for 1. I'm going to have a slope of the horizontal line -1/2. But my question is what do we put at 0? What is the slope up here? Do I put an open or a closed circle up there for the slope? Well, I don't know what the slope is up there because on the left side it's 1, but on the right side it's -1/2. So what we're going to learn is that at a sharp point, the slope is undefined because we don't know the slope there. It might be 0, but I mean, it could be that or that or that. So what we're going to do is we're going to put an open circle where they meet. Okay, let's keep going. Let's find f prime. F prime is 1, but on what interval? F prime is 1 on the interval -2 to 0. So I'm going to draw a horizontal line at 1. Okay, let me go back to my colors here. I'm going to draw a horizontal line at 1 from -2 to 0. But make sure you put your holes there. Okay, we do not equal the points there. All right, my last one. F prime equals -1 on the interval. I can't really tell where that one stops, so I'm just going to say -infinity to -2. So I'm going to put a tick mark down here on -1, and that's where I'm going to start my open circle and continue this way. Now, you're not going to have to do this a whole lot, but one thing you do want to realize is that this derivative went down 1 degree. It was a linear function and then it went constant because that's going to help us on this next problem. All right, let's try example 2. I want you to sketch a graph of g prime using the graph of g. Okay, so I'm going to give you the graph of g again. We're going to have the point, let's say 1, 2, 1, 2, 3. Let's try there. That's the graph of g. Now, I moved it up a little bit from my notes because I noticed on the quiz last year people got a little stuck because that 0 spot. So, let's look at g. G is a quadratic. And so we said for my derivative, put a little note here. The derivative goes down 1 degree each time. And so for my derivative, if I was quadratic, if I go down 1 degree, my g prime is now going to be a linear function. All right, so whatever I draw for g prime, it has to be a line. Now, I know some things about my line. I know that g starts out decreasing right here. And because of that, the slopes or the derivatives are going to be negative. When g is decreasing, its derivative or its slope is negative. So my graph starts out negative below the x-axis. Then we have a minimum. So what's the slope there? That slope is 0. When g has a min or max, g prime equals 0, or technically we're going to learn undefined, like that sharp point we saw in the last one. Okay, But because of that, it's going to hit the x-axis. It's going to equal the x-axis. And then g starts increasing again. Notice here, g starts increasing. So when g is increasing, g prime is going to be positive above the x-axis. So when I start drawing g prime, and I'm going to even label it g prime over here, I need to start out below the x-axis. And then I have to hit 0. Where do I equal 0 at, though? It's right here at this minimum. So because you have a min at x equals 2, g prime is going to equal 0 at x equals 2. I don't care what the y value is there. I just know at x equals 2 over here, my derivative g prime is supposed to equal 0. I'm supposed to start out negative and then go positive. And that would be how I'd want to draw g prime. Okay. Even though I don't have another one of those in the notes, let's call the next one part B, and I want you to try this again. All right, given the graph of g, draw g prime. So I'm going to go over here. Okay, so at, let's say at 3, negative 3, 1, I want you to draw a parabola opening down. This is the graph of g. All right, I would like you to draw the graph of g prime. So if you need to, pause the video, and I want you to try it on your own. Okay, now let's talk through it. G is quadratic. That means that we are graphing a linear function. Also, g had a maximum at x equals negative 3. So that means g prime is going to equal 0 at x equals negative 3. Remember, where g has a max, its derivative is 0. So at negative 3 over here, 1, 2, 3, I'm going to hit 0. G prime starts out increasing, so the left side should be positive, and then the right side should be negative. That would be a good interpretation of what the derivative graph would look like. All right, let's keep trying some more. Let's go to example 3. Using the graph, find when g prime is positive, g prime is negative, and g prime equals 0. Then find when g is non-differentiable. We'll write down what that word means, don't worry. So, non-differentiable, that means the derivative does not exist. We cannot find a derivative. Now, we don't really say d and e. We say d and e for limits. So we're going to use that loosely here. So one spot that we know that the function's non-differentiable is if you have a sharp point. Not like a curve, but an actual where two lines or two different functions meet. Okay, because we have two conflicting slopes. Okay, we're going to see another spot is going to be where we have a vertical asymptote. Okay, all right, so this graph is given to you. So let's go ahead and draw an XY axis. I need you to go out 2 or 3 in each direction. We're going to put 2 vertical asymptotes on the graph. One of the vertical asymptotes is at positive 1. The other one is at negative 1. Okay. We are going to put a point at 0, 1. Draw a parabola up. We are going to have the very left side hover. And we're going to have the very right side hover the opposite. Now, we've seen these graphs all the time for limits. So now I'm asking you about the derivatives, the slopes. Okay, I already see where g prime is 0. So if you need to, get out another color so you can mark this up. Remember what we're looking for. G is decreasing, means that g prime will be negative. G increasing means that g prime will be positive. G having a max or min means that g prime is 0. And later we're going to learn or undefined, because a sharp point can also be a maximum and g prime is undefined there. So let's start with g prime undefined, or g prime equals 0. G prime equals 0 at x equals blank. Where do you have a max or min in the graph? And hopefully you can see it's at 0. Because g has a minimum. And we're just going to write those little justifications there. All right, we're going to say that g prime is, let's go with negative first. Now, notice it's not going to be an x value. It's going to be on an interval. So where is this function decreasing? Where would you draw a tangent line with a negative slope? So I'm going to come over to the graph. I would draw a negative slope here. So I'm going to say from negative infinity to that vertical asymptote, which is -1, union. Where's the next time we're decreasing? Well, it looks like right away I'm decreasing. So from -1 to 0, because at 0 we start increasing. I think that might be the last time. Nope, right over here. I'm decreasing this whole time. So union 1 to infinity. Because g is decreasing. And add that justification there so you can have it in your notes. All right, we're going to say that g prime is positive on the intervals blank. So let's go ahead and look up, where is my function increasing? And it's only one time. There's only one spot where my function is increasing, and it's right here. So we're going to say from 0 to 1, because g is increasing. Now, where is g non-differentiable? Anytime you see a sharp point, where are we not able to find the derivative? Well, hopefully you can see g is non-differentiable at x equals -1 and +1. But why? Like, what's our main reason there? Because I need a because here. It can't just be because Miss Bolton said so. And the main reason here is because g is not continuous. That's a huge point. If you had a breakup or a hole here, I would not be able to find the slope at that right here, at this x value. It'd be impossible. Okay, so if my function's differentiable, then that means that it's continuous. If you can already find the derivative. So this is actually its own theorem now. And your book, we're not going to use theorem 3.1, but your book likes to call it that. And this is actually a pretty big point that we're going to use a lot. Big star. If f is differentiable at a certain point, if f is differentiable at x equals a, then f is continuous. So if you know that you can find the derivative there, then you know that it's continuous. Will that work if we flip-flop them? If f is continuous, then is f differentiable? So just because you're continuous at every point, does that mean you can find the derivative? Well, and again, in class we talk about this a lot. But no, think about those sharp points. I'm continuous there, but I'm not differentiable there. So this actually won't work. Don't erase it, cross it out, knowing that won't work. What you can do is you can say, if f is not continuous, then f is not differentiable. So if you're not continuous there, then you're not differentiable there. But this top one is the main one that we're going to use. So we're going to say this all the time. Differentiability implies continuity. If your function is differentiable, then we already know that your function is continuous. It's already proven. All right, let's go ahead and try a couple more examples with this. All right, let's try example 4. Determine when f is non-differentiable. All right, I'm going to give you a first quadrant graph, and we're going to go 5 in each direction. You might need to make your graph just a little bit bigger than mine because we're going to be drawing in it. Okay, I want you to put a point at 2, 1, and then a hole at 2, 3. We're going to put a point at, we're going to put a hole at 5, 1. And we're going to have to do our best drawing this because it's going to get a little tricky. All right, draw an arrow up. I don't really care where that goes. All right, actually go ahead and put a point at 3, 0 just so we can see it. All right, so we're going to do a nice curve, go up till we hit a sharp point, and then go this way. So where is f not differentiable? Well, one place you can look are any discontinuities. I see 2 discontinuities. I see one at x equals 2, discontinuity. So f is non-differentiable at x equals 2 and 4, or 5, Anywhere else? Yeah, right here at that sharp point, right there at x equals 4. So those are the main things. Discontinuities and sharp points are the main reasons, but there's actually going to be one more reason. So we actually may as well just write it down right now. All right. When is a function not or non-differentiable at a point x equals a? And I know x equals a is not a point, but again, we're talking loosely here. So we've talked about 2 ways. You are not differentiable, 1, if f is not continuous at x equals a. You're not continuous, you're not differentiable. Number 2, also, if you have a sharp point. Two really bad conflicting slopes that are not the same. Okay, there's actually going to be one more way we could have an undefined slope. What else? Because that's what really non-differentiability means. The slope is undefined there. So when else do you have an undefined slope in Algebra 1? Oh, well, that's going to be our last reason, and you don't see this one too often. If f has a vertical tangent. Let's write it out, vertical tangent, aka your slope is undefined. Okay, if your slope is undefined, f is non-differentiable there. It can't be. So we can even think about a little picture of what that would look like. Again, you don't see it a whole lot, but let's say you had a function on its side, and again, I don't like the way I'm drawing it. Right here, if I keep drawing tangents, at some point here, this tangent line is wanting to go vertical, and I don't know how to put the tangent. Do I put it on the left side or the right side? Anytime that tangent line would have to go vertical for you to have to draw it, Okay, aka another way to say it is that the limit as x approaches a of f prime of x would equal infinity plus or minus infinity. Okay, that means that your slope is undefined. All right, let's get one more example in for this section, example 5. Using the graph, find when f prime equals 0. F prime of x, I should stop doing shortcuts. Okay, so I'm going to go ahead and give you a graph. This was given to you. You have to go out to 3 in each direction. I would like you to draw a vertical asymptote at 2 and -1. We're going to put a point at 1, 1 and draw up. Draw a little parabola there for me. We're going to draw 2 more parabolas. We're going to put one at -2, -1. Okay, I know this isn't super realistic, but we're trying here. And then we're going to go to -3, -1. Find when f prime equals 0. Well, for me, this should be super easy. F prime equals 0 anytime that f has that max or min. Not anytime, because you could have that sharp point and then f prime is undefined. But for f prime being 0, it means I'm looking for that maximum or minimum. I always draw my tangents. I could draw a slope of 0 here, here, and here. So let's put a little spot. Draw horizontal tangents. That's what you're looking for there. And so that happens, okay, your slope is 0 at x equals -2, 1, and 3.